Hello everyone, welcome to another problem session. So today we have a Biot-Savart law, but the geometry over which the current flows is amenable to polar coordinates. Okay, so it's a circle. It could have been just an arc, but I'm doing the entire circle in this problem. So often the problem is just given as a circle like that, or it could be like this, and we are given current comes in, goes this way. So you need to find say from A to B to C to D, and then say this is L1 and this is L2 and this is some R, and that's the point P at the center. So you need to find what's the magnetic field there. So you get one from here, one from here, and one from here. Okay, so and you can add them up. So there are various versions of what we're going to do where you can apply our approach to. So if you know how to do this, here is a law, which is of course mathematical. Of course, this is going to be mathematical. When I say mathematical, means it's going to require you to think calculus. There's no other way to do it, and no other way to apply this law. But there are ways to guess the answer, okay, without using this, because there's so much symmetry in the situation. But I'm going to just say, let's try to see how we can mathematically apply this law. Okay. All right. So if you know how to do it, go ahead and do the work and then come back and see what I've done. Okay. So first thing I'm going to do is, just because this is formal, you know, this thing is formal, I need to have something I can integrate and actually put the integral. So so let's look at an element. So this is the element, that's dl. So that's dl. Well, we will have a vector. So usually it's easy to work with a coordinate system. Let's call it x and y coordinate system, and the z coordinate is coming out. Z coordinate is coming out, right? So you might draw it like that. Chemists will draw like this. You know, z is coming out. Let me erase that part. Okay, so this is in the plane xy plane, and maybe this is the angle theta. Then this vector in this direction, you can say this vector is 90 degrees like that. So it will have this is theta, this is 90 degrees, and so this will be you know, the whole thing is 180 degrees minus 90 degrees minus theta. So this is like a 90 degrees minus theta over here. And so I want to know the direction of this. I want to know unit vector along that direction to make a dl. So dl is how big it is, where this is, if this is r, and we will just say d theta, so it's d theta, and then there is a unit vector, and I will say this is like a minus sine theta I hat plus cosine theta j hat. So if theta was 0, then this is, if it was over here, it's going to point it that way, right? If DL was over here, it's going to point it up. That's correct. If the DL was over here, it's going to point to the theta will be 90 degrees, and this negative x-axis. So this is checks out a couple of points. So this is the direction, and this is a unit vector. This is a length is equals to 1. So this is a unit vector along DL direction. So this is a DL vector. And so we got that. We need to know point P from here. So let's draw this out again. So I'm over here, and this is the point P, where we want, P is the place we want the magnetic field at. So we want that, that's the R vector DL to P direction, right? So it's kind of like that. So R vector DL to P, and unit of that will be this guy, and magnitude will be that guy. So this together you can say is R vector divided by R cube, because the unit vector will be just R vector over R. That will mean this thing over here will be like this. So I don't need to really just get that. I can put this over there and replace that over there. That's usually a better strategy. So let's do this R. So what this R vector will be, oh, this is just a radial vector, negative. So it has a negative R. So this direction is that direction. If it was that direction, it's going to be cosine theta I hat plus sine theta j hat. So this is the magnitude of this R, and with minus, this is the direction. So the way I did it is, I said from here to here, that will be just this guy direction, and so flip it, put a minus sign out there. So that's what I did. Okay, so if I'm this and I'm getting DL cross R, so let's do that, DL cross R, and I'm just gonna say, I'm not gonna write that every time. So minus R square d theta. So I have this times this, but it is a cross product. So this with this will be 0, because I hat cross I hat is 0. Remember, I hat cross I hat is 0, and I hat cross j hat is k hat, and j hat cross j hat is 0, and j hat cross I hat will be minus k hat. So these are the things you should remember from cross product. So this with this zeros, I go with that. So this is minus sine square theta j hat, and this with that will be minus cosine square theta j hat. This with that will be 0. So this is just a minus 1. So this is like R square. This minus 1 will kill minus. So just R square d theta. Very nice. Okay. Downstairs, the magnitude of that is R square times the magnitude of that, and that's just equal to R. That we already knew that's R, so we don't need to do that. This is the magnitude, so I don't need to do that. So now B at the center, B at the magnitude and direction of that magnetic field that I'm going to get at the center should be equal to just mu naught the steady current. So remember, this current is steady current. So steady current, not just when you turn the switch on. When you turn the switch on, you have to wait a little bit for the current to steady up. Okay. And I'm going, this is a formal integral, but I'll see what the integral is. So numerator is R square d theta, denominator is R cube, because we're using this. Denominator will be R cube. We use R, full R instead of unit vector. And so this is just now this shows us what the integration variable is, and that integration variable goes from theta equal to 0 to, if I come back, 2 pi. all the way to 0 to 2 pi. So that's where I get limits and things like that. If I was going only halfway, if this was halfway, a quarter, we'll have limits accordingly adjusted. And this does not depend on theta. So this is just a very simple integral, mu naught I over 4 and this is k hat, right? This is it's k hat. So this is k hat. So k hat doesn't depend. So k hat's gonna come out mu naught I 4 pi r times 2 pi. So this is k hat. The answer is k hat mu naught I over 2r. So that's the answer. See, pretty easy to almost guess just from the dimensional. The 2 may be hard to guess, but other than that, it turns out to be pretty easy. I hope you learned something from this example, how to set up in a polar coordinate, how to actually start from the very basic experimental. This is a experimental answer, right? This is comes from observation on a steady current. So this is empirical law. When you have a finite current, like finite size circuit, if you have finite size circuit, then you only have Biot-Savart law to work with. But if you have circuits with some symmetries, etc., we're going to learn that the choice that we're going to make circuits with certain symmetry, and we're going to do more problem of that. We're going to do what's called Ampere's laws. Here it doesn't have that kind of symmetry. We will learn about those symmetries when we study Ampere's law. But if you have those symmetries, this is where you go. It's almost like what you did in electrostatics, right? When you have certain symmetry, you go to the Gauss's law before you do the integrals and things like that. And here is almost a kind of parallel situation. The problem is the Ampere's law is a little bit harder to implement than Gauss's law, but we will do this in a future video. But here you just have to do the integral. There's no other way, short of just guessing the answer. So of course this just guess from dimensional analysis, you can guess that, but to guess 2, you really have got to do all this work. All right, okay, I hope that you enjoy this kind of mathematical analysis. All right, if you haven't subscribed, please subscribe to this channel. Tell your friends to subscribe to this channel. Maybe they all will learn some physics. And if you enjoy, please hit the like button. You can get more out this kind of direct analysis of physics in my website, physicsbootcamp.com, not .com, physicsbootcamp.org. It's been up and running for a while, and quite a few people use it daily. And see you in another video. Take care. Bye.